Yeah, question number 3.1. The question given is arrange the following metals in the order in which they displace each other from the solution of their salt. Okay, so aluminium, copper, iron, magnesium and zinc. Okay, these metals are given. Now we need to identify, or we need to arrange these metals in the order in which they displace each other from the solution of their salt. Okay, suppose if we have aluminium ion solution, right, if we put a copper rod, can copper displace aluminium ion or not? Okay, I have told you for this what you have to do is you have to see the reduction potentials, SRP values, right? I have told you that if SRP value is high, okay, you know very well, if you can see the standard reduction potentials. Okay, standard reduction potential, that is SRP. Okay, for the metal ion become metal, right? Metal ion become metal. This is called reduction. We also say simply this as SRP. What is SRP? Standard reduction potential of the metal. Okay, if SRP value is high, suppose if SRP value for a metal, for a particular metal ion is high, that means the metal can undergo reduction easily. The metal can undergo reduction readily. Okay, if SRP value is low, then the metal will undergo oxidation easily. So now what is the point here is, suppose I have a solution. I have a solution containing some metal ion, say M1 or Ma, some metal ion, okay, Ma, having some charge. Now I am going to immerse a metal rod of a different metal Mb. Now the question is, can Mb displace Man plus? Okay, you have metal ion in the solution. Can this metal displace this metal ion in the solution? What you have to do for this metal should undergo oxidation readily. Okay, in this solution the metal should undergo oxidation readily. For oxidation, you know very well, for oxidation SRP value is low. Okay, so if any metal has low SRP compared to the metal ion in the solution, then that metal can displace. Okay, so now what I'm going to do, first I will arrange these metals in the SRP values of these metals in the decreasing order. Okay, see here we have aluminium. Let me just go through the table and I will tell you the values. I am using some standard books for this purpose. Yeah. Electrochemistry.
Sir, how does Mg undergo oxidation?
Why, ma? It is an alkaline earth metal, no? It will undergo oxidation, form Mg2 plus 2 electron. Am I right? All metal undergo oxidation readily, but now the question is, among the 5, okay, or we have to arrange these 5 metals in the increasing order of their the tendency to undergo oxidation. For that you have to see the SRP value. If SRP value is low, that metal undergo oxidation readily. If the metal undergoes oxidation, then it can replace the other metal ion present in the solution. Okay, that's the idea. Is this clear?
Yes, sir.
Yeah. 1 second. Yes, I got. So I'm just going to give you the order in which the SRP values of these metals are available. Okay, Aluminium, copper, yeah, SRP value for copper is plus 0.34. Let me just note down here, plus 0.34 volt for copper, and for aluminium SRP value is minus 1.66 volt, and for iron, in iron 2 plus solution, iron become iron 2 plus. Iron 2 plus become iron. The SRP value is minus 0.44 volt, and for magnesium the value is minus 2.37 volt, and for zinc is minus 0.76 volt. Minus 0.76 volt. Now among these, the least value is for magnesium. Okay, magnesium has the lowest value, so SRP values I am arranging in the increasing order of SRP value, right? I am in the decreasing order of SRP value. So in decreasing order, this is positive, so first one is copper, okay, then the next one is iron, then the next one is aluminium, no, zinc, then the next one is aluminium, then the next one is magnesium. Okay, I have arranged the metals, okay, in the decreasing order of their SRP values, and you know very well the one which is having lowest SRP value can displace the metal ions of these. Okay, so magnesium can displace cupric ion, magnesium can displace ferrous ion, magnesium can displace zinc ion, magnesium can displace aluminium ion. Okay, so what is the answer? The answer is this. So arrange the following metal in the order in which they displace each other. Okay, so magnesium can displace copper, so the correct order, right? Order in which the metal can displace metal ions of other metal. Okay, order in which the metal can displace the metal ions of other metal. So what is the order? The order is this: magnesium can displace, okay, magnesium, as since it has lowest SRP among these five, magnesium can displace metal ions of any of these five. Okay, so magnesium can displace any of this. Then aluminium can displace cupric ion, ferrous ion and zinc ion present in the solution. Okay, then zinc can displace cupric ion and ferrous ion present in the solution. Then iron can displace cupric ion present in the solution. Okay, so this is the order. That is why you should not keep aluminium ion solution in a magnesium container. You should not keep zinc ion solution in magnesium container. Okay, because it will easily displace. Therefore, the metal will dissolve. Okay, so it is not advisable to keep cupric ion solution in magnesium container, or to keep cupric ion solution in a zinc container, or to keep ferrous ion solution in aluminium container. Okay, it's not advisable. Okay, because the metal can displace. Right, take note. Is this clear?
Yes, sir.
Yeah, take note. So this is question number 3.1. Now question number 3.2. This question number 3.2. Given the standard electrode potential, students, observe carefully. If they say electrode potential, it should be reduction potential only, but it is given clearly that K plus becoming K. For this, the electrode potential is minus 2.93 volt. Then Ag plus silver ion becoming Ag. For this, the potential is plus 0.80 volt. And for mercuric, Hg2 plus, right? For mercuric ion becoming mercury, the reduction potential value is given, which is plus 0.79 volt. And for magnesium 2 plus becoming magnesium, the value given is minus 2.37 volt. Then one more ion is given, chromium 3 plus becoming chromium. For this metal, the value given is minus 0.74 volt. And the question is this: arrange these metals in the increasing order of reducing power. Okay, reducing power means how easily this metal can reduce the other metal. That is called reducing power. Okay, or reducing property. Right? Now, you know very well, if any metal readily donate electron, then that metal can act as a good reducing agent. So here reducing power, right? In the order of reducing power they are asking. Here reducing power means, what is the meaning for the reducing power? Reducing power means, okay, how easily the metal can donate electron. Okay, so we can say that it is a reducing agent. Reducing agent. Okay, a reducing property. For reduction, students observe carefully. For reduction, the metal should donate electron readily. That means the SRP value should be low. Right? If SRP value is low, then the metal can act as a good reducing agent. Then it is a reducing agent, Ra. If SRP value is low, then it is a good reducing agent. Now, among the 5, see which one has the lowest SRP value? Lowest SRP value is for potassium. Therefore, potassium can act as a good reducing agent. Right? So I am just arranging in the increasing order. Potassium is a good reducing agent. Right? Then next one is magnesium. Then next one is, after magnesium, I am just arranging in the increasing order of SRP. SRP is lowest for potassium, so it is a good reducing agent. The next metal is magnesium. Okay, compared to potassium, magnesium has a little higher SRP value. Okay, higher SRP value means reducing power is less compared to potassium. Okay, then after magnesium we have chromium. After that we have silver, then mercury. Okay, take down. Is this clear, student? Reducing power here
Yes,
means how it can donate electron to the other species. Okay, how it can donate. For electron donation, SRP value should be low. SRP value should be low. So among the 5, for potassium the SRP value is minus 2.93. Therefore potassium supposed to be the good reducing agent among the 5. Next one is magnesium, next one chromium, next one silver, like that. You have to arrange. Then question number 3.3. Depict the galvanic cell in which the reaction zinc solid. Okay, let me write the reaction. 3.3. Depict the galvanic cell in which the reaction, some reaction is taking place in a galvanic cell. Zinc solid reacts with the 2Ag plus aqueous, giving zinc 2 plus aqueous and 2Ag solid. Okay, some reaction is taking place. This reaction is taking place in a galvanic cell, and they are asking few questions. Question number 1: which of the electrode is negatively charged? Okay, now reaction is given. You have to identify the electrode. Very simple. First you draw a salt bridge. Okay, here see zinc undergoing oxidation, correct? It loses electron and become metal ion. If any metal become metal ion, it is oxidation. And you know very well oxidation occurs at the anode. So always while writing cell on a paper, first to draw salt bridge. In the left hand side you should put anode, and in the right hand side you should put cathode. So anode, oxidation occurs at the anode. So which is undergoing oxidation? Zinc is undergoing oxidation. Therefore zinc solid become zinc 2 plus ion. So this is the anode. And what about the cathode? Ag plus becoming Ag. Ag plus ion gaining electron and become Ag. Okay, when metal ion becomes metal, it is reduction. So here Ag plus in aqueous medium, okay, and become Ag solid. So this is the reduction reaction. So this is the cell in which this reaction takes place. Okay, this is the representation of the cell in which this reaction takes place. And you know very well this is anode, this is the anodic compartment, and this is the cathodic compartment. Okay, and you know very well in galvanic cell anode carries negative charge and cathode carry positive charge. Right? So the question number 1 is which of the electrode is negatively charged? It is the zinc electrode. Zinc immersed in zinc ion, that is negatively charged. Okay, so zinc immersed in zinc 2 plus aqueous, right? This electrode act as the negatively charged electrode. Negatively charged electrode. Very simple, because that's anode. Okay, is this clear, student? Is this clear? Hello?
Yes, sir.
Take two. Then second question asked in 3.3, that the carriers of the current in the cell is the carriers of the current in the cell. The current is carried by electron. Okay, the current is carried by electron. So electrons carry the current. Electrons carry the current. Current externally. Externally electrons carry the current. Right? Then for neutralization, the ions present in salt bridge, okay, will move in the respective solutions, and that carries the current in the solution. Okay, but you just mentioned this one, this is sufficient. Then one more question they have asked, that is individual reactions at each electrode. Individual reaction, yes, it is available already. So what is the individual reaction at each electrode? Yeah, question number 3. Very simple. At anode, what is happening? Zinc solid giving or losing 2 electron and becoming zinc ion. This is the reaction takes place at anode. Then at cathode, Ag plus ion present in solution gains electron and become Ag solid. So this is the reaction takes place at the individual electrode. Okay, overall reaction is this. Okay, here they have given overall reaction, but the individual reaction at the electrode is this. Okay, yeah. In individual, while writing individual reactions, students, you need not balance the number of electrons. It's not required. While writing overall reaction, okay, you should balance the number of electron and you should cancel that. Okay, take note. Is this clear, students? Hello, students, am I audible? Hello?
Yes, sir.
Yeah. Right.
Yes, sir.
Yes. Then so this is question number 3.3. Then question number 3.4, calculate the standard cell potentials of the galvanic cell. Yeah, let me do it. Question number 3.4, calculate the standard cell potential. They are asking you to calculate standard cell potential, and here cell reactions are given. Okay, cell reactions, number 1, cell reaction is given: 2 chromium solid plus 3 cadmium 2 plus aqueous, giving 2 chromium 3 plus aqueous plus 3 cadmium solid. This is the reaction takes place in a cell. Now what we have to do for this reaction, we need to find out the E0 cell. Okay, and first what you have to do, first you find out which is anode, which is cathode. Okay, here it's very clear, chromium become chromium 3 plus, so it undergoes oxidation. That means chromium immersed in chromium 3 plus act as the anode. So in the salt bridge, chromium becoming chromium 3 plus ion. Okay, so this is the oxidation reaction. And what is the reduction reaction? Cadmium 2 plus becoming cadmium, that is a reduction reaction. So cadmium 2 plus aqueous become cadmium. Don't worry about these numbers. Okay, these numbers is supplied here. It is for the balancing purpose. While writing cell representation, you need not worry about that. Okay, just take what is the rod, what is the metal, and in which solution it is immersed. Okay, now see, this is anodic compartment and this is cathodic compartment, right? This is anode and this is cathode, right? And you know very well, cell potential or standard cell potential is nothing but standard reduction potential of cathode, okay, minus standard reduction potential of anode. I'll just put here this, or E0 right, E0 left, anyway. Okay, you can write whichever way is comfortable, you can write. So what is the reduction potential at the cathode? E0, cadmium 2 plus becoming cadmium, this is the reduction potential, minus at the anode side, the reduction potential is, we have tried reduction potential, so listen, observe this carefully, chromium 3 plus becoming chromium, this is the reduction reaction. Okay, now we need to find the values of these from the table. Okay, in the examination they will provide, but now I will give you the value from the table, right? So from table, the reduction potential for cadmium is minus 0.40 volt, minus reduction potential for chromium 3 plus becoming chromium, chromium 3 plus becoming chromium, the value is minus 0.74 volt. Right? So what is the cell potential? Standard cell potential, very simple, minus 0.4, minus or minus become plus 0.74. Okay, so if you subtract, right, we get 0.34 volt. So plus 0.34 volt is coming. This is the standard cell potential, right? Standard cell potential for a cell in which this reaction occurring. Okay, and one more reaction is given. Students, I will just leave that question to you. You try to find out the standard cell potential for that cell. Okay, will you do, students?
Yes, sir.
Yeah, right. Take it. So this is question number 3.4. Then let me go to the next question. Question number 3.5. 3.5. Actually, this is the question which we need to focus. Write the Nernst equation and EMF of the following cell at 298 Kelvin. Okay, so we need to write the Nernst equation. question number 3.4. I'm sorry, 3.5. Yeah, SL is given. 4 questions are given here. So let me take the first one. Magnesium solid immersed in magnesium ion solution of concentration 0.001 molarity. Salt-bridge. Then cupric ion solution of concentration 0.0001 molarity. A copper rod is immersed. Okay, this is the question given. Now what we have to do, we should write the Nernst equation for this cell and we should calculate the cell potential. Okay, yes, how to do that. And temperature is given here. Temperature is 298 Kelvin. Okay, so it is very simple. What we have to do, first we should write the cell reaction. Okay, what is the cell reaction here? Magnesium becoming magnesium 2 plus. So Mg become Mg 2 plus and release 2 electron. Okay, this is the reaction taking place at the anode. Okay, we need to put solid, aqueous and all. Let us not worry about that now. Then in the right hand side electrode, cupric ion become copper. Cupric ion gains 2 electron and become copper. So this is the reaction occurs at the cathodic compartment. Now what's the overall reaction? Since the number of electrons are equal, so you can write the overall reaction directly. What's the overall reaction? Magnesium solid plus cupric ion aqueous giving magnesium ion aqueous and copper solid. Okay, so this is the overall reaction, cell reaction occurring in this cell. Now I am going to write cell potential for this, but I have told you before going to calculate cell potential, first you should calculate E naught cell. Okay, so what's the E naught cell? Okay, first I'll write the Nernst equation, then I'll tell you why we need to calculate E naught cell. See, what is the Nernst equation for this? Nernst equation for this reaction is E cell is equal to E naught cell minus actually we should put 2.303 RT by NF, but temperature is given as to 298 Kelvin, which is 25 degrees Celsius. Okay, therefore that constant becomes 0.0591 divided by number of electron transferred in the overall reaction is 2 into log base 10, right? Product concentration, let me go to the product side. If any substance given as a solid, for that concentration is 1. You need not worry about that, and you should consider only the ions, right? So concentration of magnesium ion divided by, in the denominator we should consider reactant, and reactant magnesium is solid, so for this the concentration is unity, you need not consider this. And for cupric ion we should consider the concentration of cupric ion. Okay, so here see, you require E naught cell. So what is the E naught cell, right? So first let me calculate E naught cell for the reaction. For the cell, E naught cell is nothing but E naught cathode, right hand side electrode, minus E naught anode. Okay, so in the for cathode, the cupric ion become copper. The SRP value, the values will be given in the examination, but now in the book the values are in the question, the values are not given, so I'll just take the values from the table. For copper 2 plus becoming copper, the reduction potential is plus 0.34 volt minus, and for magnesium, for the reduction potential for magnesium we should consider only reduction potential, though oxidation takes place here. Okay, you should consider only reduction potential for this formula. So the value is minus 2.37 volt. So minus of minus become plus, so this is also plus, so you just add the 2. 7 plus 4 11, 7, then 2, so 2.71 volt. So this is the cell potential, E naught cell for this particular cell, right? Take down. we have calculated E naught cell. Now substitute this E naught cell here and substitute the concentrations given, okay, and calculate the value. Simple. Is this clear, student? Any doubt?
No, sir.
Yeah, take note. Yes. So how to calculate the cell potential? E cell equal to E naught cell value we have calculated, which is 2.71 volt, 2.71 minus 0.0591 by 2 log base 10. In the numerator we have concentration of magnesium ion, denominator we have concentration of cupric ion. Okay, what is the concentration of magnesium ion? Magnesium ion concentration is 0.001, which we can write directly as 10 power minus 3. Correct. And cupric ion concentration is 0.0001, which is nothing but 10 power minus 4. So magnesium ion concentration is 10 power minus 3 and cupric ion concentration is 10 power minus 4. Okay, so what we get is 2.71. Let me take this value as 0.06. 0.06 by 2, you get 0.03 log base 10. If we bring 10 power minus 4 to the numerator, it becomes 10 power plus 4. So 10 power minus 3 into 10 power plus 4 become 10. Log 10 base 10 value is 1. So this value is 1. Therefore 2.71 minus 0.03, if I subtract, I'll get 11, 3, 8 and 6 here, then 2.68 volt. This is the cell potential for this cell. Is this clear, student? Students, is this clear? Any doubt here?
Yes, sir.
Yeah, take note. Like this, few more cells are given, okay, in question number 3.5. So I have worked out for question number 1. For question number 2, 3, 4, you try to do it, okay, and if you get any difficulty, you can ask me in the next class. Okay, now so these are all a few questions given in the book. Then what is the relation between equilibrium constant and standard cell potential? This is another important one that you need to consider. Okay, relation between standard cell potential E naught cell and equilibrium constant K, capital K. It represents thermodynamic equilibrium constant. What is the relation between these two? Students, observe carefully. Suppose I'll consider a cell reaction. Consider a cell reaction of the type, say for example, say X moles of A reacts with the Y moles of B, giving M moles of C and N moles of D. Some reaction. A and B are reactants, C and D are products. Okay, and this reaction takes place in a reversible manner. Now, students, in Nernst equation, what we do, see, before while deriving Nernst equation, we started like this, right? For any chemical reaction, we can write delta G as delta G equal to delta G naught plus RT ln Q, where Q is called reaction quotient. We'll write like this only. Okay. So if the reaction is not at equilibrium, then Q is nothing but the concentrations of the product divided by concentrations of the reactant. Very simple. Okay. So what is Q here? Q is nothing but concentration of C power M into concentration of D power N divided by concentration of A power X into concentration of B power Y. Here the concentrations are not at equilibrium. Okay, if the reaction is not attained equilibrium, then this is the relation, right? Now if suppose the reaction attained equilibrium, what will happen at equilibrium? Okay, if the reaction attained equilibrium, then you know very well, for any reaction, if it attain equilibrium, delta G value becomes 0. At equilibrium, delta G is equal to 0. Remember this, very very important. Delta G becomes 0. Delta G naught is not 0. Okay, delta G naught value is not 0 because delta G naught is a constant for a given reaction, okay, at a constant temperature, right, at a particular temperature, right? Now, so if I substitute this value here, and one more point, at equilibrium these concentrations become equilibrium concentrations. Okay, when you put equilibrium concentrations here, then the reaction quotient Q becomes equilibrium constant. So at equilibrium, Q becomes equilibrium constant K. So what is K? Therefore, what is K? K is equal to concentration of C power m at equilibrium into concentration of D power n at equilibrium divided by concentration of A power x at equilibrium into concentration of B power y at equilibrium. Very important. These are all equilibrium concentrations. Here the concentrations are not at equilibrium. If the concentrations are not at equilibrium, then this ratio is called Q. Once the reaction attained equilibrium, okay, now we should put equilibrium concentrations here. Okay, this ratio containing equilibrium concentration is called equilibrium constant. So Q becomes K at equilibrium. Therefore this equation becomes, so delta G is 0 at equilibrium and delta G naught plus RT ln, in the place of Q I'll put K, where K is called equilibrium constant. And what is delta G naught? Delta G naught equal to minus RT ln K. Okay, very very important expression. Take down. Delta G naught equal to minus RT ln K. Delta G naught is nothing but standard free energy change, which is equal to minus RT ln K. R is gas constant, T temperature in Kelvin, K is equilibrium constant, thermodynamic equilibrium constant. Okay, if you convert ln into log base 10, okay, if you convert ln into log base 10, you have to multiply this by 2.303, right? So minus 2.303 into RT into log base 10 K, right? You'll get an expression like this. Then we also know that delta G naught has a relation with the E cell, right, or E naught cell. What is the relation? We know very well. Delta G naught equal to minus NF into E naught cell. We know this. Therefore, the above equation becomes, so in the place of delta G naught I'll put this minus NF E naught cell equal to minus 2.303 into RT log base 10 equilibrium constant. This minus n cancel. So what is E naught cell? E naught cell equal to, okay, I'll bring this NF to the right hand side. So 2.303 RT by N into F log base 10 K. This is the relation between standard cell potential and equilibrium constant K, right? Take down. And here at 25 degrees Celsius, at 25 degrees Celsius, 25 degrees Celsius means 298 Kelvin. At 25 degrees Celsius, okay, this value 2.303 by RT by NF, except N, the remaining things are constants. So that constant, we have already seen that the constant is 0.0591 over N into log base 10 K. This is the relation between standard cell potential and equilibrium constant. Okay, take down. Very useful relation and very very important for competitive examinations. Okay, take down. Is this clear, students? Any doubt?
No, sir.
Yeah. Now we'll do a few problems making use of this concept. It's a question given in the book. There is example 3.2. Example number 3.2. Okay. The question is, calculate the equilibrium constant of the reaction. Some reaction is taking place in a cell. Copper solid reacts with the 2 Ag plus aqueous giving copper 2 plus aqueous and 2 Ag solid. Okay, some reaction, okay, some equilibrium reaction is taking place in a cell, right? We need to find out the equilibrium constant for this. So what's the equilibrium constant for this? Okay, so how to calculate? It's very simple. What is given here is E0 cell value is given. Actually, E0 cell value we need to calculate. We can calculate actually, but in the question it is given directly. Sometimes they will do like this. Okay, E0 cell value is given, and we need to find out the equilibrium constant. Okay, equilibrium constant in terms of concentration only, right? So we can also put Kc here. Right, I'm going to write equilibrium constant in terms of concentration. That's the reason why I put Kc. Okay, now you know very well temperature. One second, temperature is not given. Okay, temperature is not given. So let us assume the temperature is 25 degrees Celsius. Temperature is not given actually, but they will provide usually. Okay, since the temperature is not given, I'll take this temperature as 25 degrees Celsius. Okay, now. So what's the relation? The relation is this: E0 cell, you know very well, E0 cell is equal to 0.0591 divided by n into log base 10 equilibrium constant K. Okay, E0 cell value is available 0.46 volt, and here this is 0.059. You can make it into 6. 0.06 divided by n value. What is n? Number of moles of electron that is involving in this reaction. Okay, see, copper become copper 2. It's a balanced equation. In this balanced equation, see, copper become copper 2 plus by releasing 2 electron, right? Okay, it releases 2 electron and become copper 2 plus. So number of electrons involved in this reaction is actually 2. Number of moles 2. 0.06 by 2 into log K base 10. Okay, so if you multiply this by 2 and divided by 0.6, you will get log K base 10 equal to 2 into 0.46 divided by 0.06. Okay, so what's the value? Let me use calculator just for saving time. Okay, 2 into 0.46 divided by 0.06. I am getting an answer which is 15 point log K base 10 comes out as 15.333. It goes like that. Okay, now what's the value of K? K is equal to anti-log of this, right? So anti-log for this value 15.33333. Okay, you know very well how to take the anti-log. So see the table. In the anti-log table, you see what's the value for 0.3333, and whatever value that comes, okay, into 10 power 15 you should put. That's all, into 10 power 15, right? And the value obtained here is 3.92 into 10 to the power 15. Okay, take note. This is the equilibrium constant, right, for this reaction. Okay, so you can, if you know the standard cell potential value, yes, you can calculate the equilibrium constant for the reaction. Is this clear, student? Any doubt?
No, sir.
Yes, no, yes. Then and here let me go to the in-text question 3.4 in the book. In-text question: calculate the potential of hydrogen electrode in contact with a solution whose pH is 10. Calculate the potential of hydrogen electrode in contact with a solution whose pH is 10. Okay, hydrogen electrode is given. Hydrogen electrode which is immersed in a solution whose pH is 10. What we have to do? We need to find out the electrode potential, but it is not mentioned whether it is anodic potential or cathodic potential. Okay, usually they should mention that, but it is not given. So what we are going to do is let us consider this as a reduction. Okay, because normally reduction potential they'll expect. Okay, so I'll repeat. In the question they are asking, calculate the potential of hydrogen electrode. Okay, that potential may be anodic potential or cathodic potential, right? But usually we calculate reduction potential. So what we are going to do, we are going to calculate the reduction potential for this electrode. What is reduction potential? H plus become H2. H plus become H2 is reduction potential. So this is what we need to calculate. Okay, pH is given. You know very well the reduction reaction is H plus aqueous gaining 2 electron and get reduced to H2. H2 gas. Okay, usually we take pressure as 1 bar, and H plus concentration we don't know, but pH is given. pH is 10. Now we'll apply Nernst equation. According to Nernst equation, E H plus become H2. Reduction potential for H plus become H2 equal to E naught H plus become H2 minus 2.303 we should put. Let us assume the temperature is 25 degrees Celsius. Temperature is not given, so add to 25 degrees Celsius. Add to 25 degrees Celsius the constant you know very well, 0.0591 divided by number of electron transferred is 2 here into log base 10. In the product side we have hydrogen gas. Okay, so pressure of hydrogen gas divided by, in the reactant side we have H plus ion, so H plus ion power 2. Okay, and pressure is given, which is 1 bar, so I'll put 1 bar here. And you know very well for standard hydrogen electrode potential, okay, if I put not symbol, that not symbol indicates standard. So this is standard hydrogen electrode potential. Whether it is reduction or oxidation, this potential is arbitrarily assumed as 0. Okay, the value is 0 minus 0.0591 over 2, and since pressure is 1 here, so we'll get log base 10 1 by concentration of H plus power 2. Okay, I'll bring this H plus power 2 to the numerator. So what we'll get is 0.05. Let me write this as roughly as 0.06 by 2 to log base 10 concentration of H plus power minus 2. I'll brought this H plus to the numerator and bring the minus 2 in front. Minus of minus become plus, so you'll get 2 into 0.06 by 2. 2 cancel, so you can cancel the 2's, so I'll get directly log 0.06 into log base 10 concentration of H plus. Okay, now what I'm going to do, I'll put a minus sign in front and I'll put another minus here. So the equation, nothing going to change in the equation. Okay, because minus into minus become plus. Why I did this? Because you know very well negative logarithm of H plus is nothing but pH. Okay, so the value becomes,
Sir, isn't it 0.06 divided by 2, sir?
hello, pardon?
Isn't it 0.06 divided by 2, sir?
Yeah, but here we have minus 2, no more. In the power we have minus 2, according to logarithmic rule, we should bring this minus 2 in front, right? So minus
Oh,
or minus
okay,
become plus, and you will get 2 here. That 2 and this 2 get cancelled. Okay.
Okay, sir.
Right. Now what we get is minus 0.06 minus 0.06 into pH. Okay, or you can also write 0.0591, nothing wrong in it. That's the exact one. Okay, 0.0591 into pH. So this is the relation between, students observe carefully, this is the relation between hydrogen electrode potential, reduction potential, and the pH if the hydrogen electrode acts as a cathode. In the last class I have given the relation for hydrogen electrode acting as anode. Now when hydrogen electrode acts as cathode, if hydrogen electrode, okay, acts as cathode, if hydrogen electrode acts as cathode, then this is the relation. Okay, so pH is given. Students, this formula is very important for competitive examination. Okay, pH is given 0.0591 times pH value is 10 here. So if you multiply by 10, you will get 0.0591. Okay, this is the potential, reduction potential for the hydrogen electrode. What is the corresponding oxidation potential? Oxidation potential means H2 become H plus is oxidation potential. If you want oxidation potential, just change the sign, plus 0.591. Okay, this is the oxidation potential for the hydrogen electrode if it acts as anode. Here this is reduction potential if the hydrogen electrode acts as cathode. Okay, take note. Is this clear? Any doubt?
No, sir.
Right, ma'am, take note. Okay, and two more questions are given, they in text 3.5 and 3.6. Those things we have already done, so you just go through the question, okay, and try to do it in your own. Okay, now let me give one more important point here, students. See, we are discussing about galvanic cells. Galvanic cells, right? In galvanic cell we have anode and we have cathode. While representing the cell on a paper, we always write like this. I have told you, we write anode in the left hand side, cathode in the right hand side. Students, observe carefully. In galvanic cell we have two. In galvanic cell we have two types. In galvanic cell we have two types. What are they? One is normal galvanic cell, that is chemical cell. We say simply chemical cell. Chemical cell. Okay, chemical cell means what's the meaning? I'll tell you. Then we have concentration cells. Concentration cell. We usually divide galvanic cells into two: chemical cell, concentration cell. What's the difference? In concentration cell, students, the electrode, anode and cathode are different. Okay, right? The electrodes are different. Electrodes are different. Okay, you have different electrodes. Whereas in a concentration cell, anode and cathode are same electrodes. Here electrodes are of same type. Electrodes are of same type, but different concentrations. Different concentrations. Okay, if you have different electrodes, it is chemical cell. If you have same electrode, okay, as anode and cathode, but having different concentration, then it is called concentration cell. Okay, so remember, in galvanic cell we have two: chemical cell and concentration cell. In the case of concentration cell, students, this is very important, E0 cell is 0. In the case of concentration cell, E0 cell is 0. In chemical cell, E0 cell is usually not 0. Okay, very rarely it becomes 0, but usually it's not 0. For concentration cell, for all concentration cell, E0 cell value is 0. Okay, let me give I'll give one example. See here, for concentration cell, right? I'll take zinc solid immersed in zinc ion solution, aqueous solution of concentration say C1. Then this is my anode, and in the cathode I'll take zinc rod immersed in same zinc ion solution. Okay, but the concentration is C2 here. C1 and C2 are not equal. Okay, if C1 and C2 are not equal, then you will get some potential for the cell, and that is called this cell is called the concentration cell. Why? Because anode and cathode have same species. Okay, so this is an example for concentration cell, right? And what is the potential? Yes, we can write based on the Nernst equation. Okay, so based on Nernst equation, E cell equal to E0 cell minus 2.303 RT by, students, this equation is very simple. Let me write the reaction here so that you can easily understand this. See, zinc becomes zinc 2 plus, okay, the anode. Zinc become zinc 2 plus of concentration C1. Okay, let me write the next page so that it will be clear to you. See what happens at anode. At anode, zinc solid undergoes oxidation, gives you zinc ion of concentration C1 and releases 2 electron. And what happens at cathode? At cathode, zinc ions of concentration C2 gains 2 electron and becomes zinc solid. Okay, and what is the overall reaction? Since number of electrons are equal, you can directly add the 2. So zinc solid, okay, plus here, one second, you can cancel 2 electron, and you can cancel the same species here. So what is remaining? Zinc 2 plus ion aqueous medium of concentration C2 becoming zinc 2 plus ion aqueous medium of concentration C1. See this? Right? And what is the Nernst equation for this? See, in the right hand side we have C1 concentration, in the left hand side we have C2, right? So in the Nernst equation, 2.303 RT by 2 electron transfer takes place, so 2F log base 10, right? In the right hand side we have zinc ion concentration of C1, so I'll put C1 here directly, and in the left hand side we have zinc ion concentration of C2, so I'll put C2 here. See this, student? This is the cell potential. Here I forgot to give this. E0 cell value is 0 for concentration cell. If E0 cell becomes 0, then what we'll get? We'll get E cell equal to, let me write here, E cell equal to minus 2.303 RT by N value is 2F log base 10 C1 by C2. Right? This is the cell potential for this concentration cell. Okay, student, let me ask one question. What happens if C1 and C2 are equal? Can anyone tell me the answer?
0, sir.
Yeah, if C1 and C2 are equal, you'll get 1 here, right? C1 and C2, if you cancel, get 1. Log 1 value is 0. If this 0, then everything become, because you are going to multiply, so everything becomes 0. So when if C1 and C2 are equal, then cell potential also becomes 0. Not only E naught cell, even cell potential becomes 0. So in concentration cell, students observe carefully. In concentration cell, anode and cathode electrodes are same. If concentrations are also same, then cell potential becomes 0. The cell never work. The cell will work only if the concentrations are different. Okay, so that's very, very important. Now, second point. Listen, student. C1 is the concentration in the anodic compartment, correct? C2 is the concentration in the cathodic compartment. Now, if C1 is less than C2, what will happen? That is concentration in the cathodic compartment. This is cathodic, and this is concentration in the anodic compartment. Correct? See, I'll show you. Correct? This is anodic compartment. This is concentration in the anodic compartment, C1. C2 is the concentration in the cathodic compartment. Okay, right? If C1 is less than C2, what will happen? C1, C2. C1 is less, C2 is high. That means you will get fraction, right? 0 point something. Less than 1, correct? Positive value, but less than 1. If the log value is less than 1, student, if log value is less than 1, you will get negative. Logarithm of any less than 1 will give negative. Negative and negative become positive. So E cell will comes out as a positive value. So whenever concentration in the cathodic compartment is high, concentration in the cathodic compartment is high, you will get cell potential as positive value. Right? Take note. Is this clear, student? Any doubt? Are you comfortable with this?
Yes, sir.
Yeah, right. Okay, I stop here.